Okay, welcome to the afternoon session. And
okay, so the point is that JJ has a fantastic talk ready for all of you. And we felt like we are here, but we are not getting enough questions on the specifics to neutrino flavor transformations, which is an unfamiliar subject perhaps to many who work in pure astro or hydro. And so we're here, we're happy to have an informal Q&A after this talk ends, or we go drink coffee. So those are the choices.
Or we drink coffee and have a Q&A. Yeah.
So, if you have questions, this afternoon is a very good time to ask in a more informal setting than official talks. Right. So
yeah. So greetings, everybody. For those of you who don't know me, I'm JJ Cherry. I'm a postdoc at Los Alamos National Lab. And today we're going to do something a little bit different from the previous 2 days of workshops. Just because it's fun to get a piece of code and run it and have some results. But not every problem in your life is going to have a code already written to solve it. So what we're going to do here is take a problem that not a lot of you are familiar with. There's a few of you in the room who know what's going on with this problem, but this is going to be, seeing under the hood here is going to be kind of a new experience for a lot of the rest of you. And so we're going to sit down and spend a little time kind of developing a program for how to solve a new problem that we haven't seen before. So this is originally based on work that Huayu Duan, George, Joe Carlson, and Yongzong Chen did back in 2006. They were kind of the pioneers of this calculation back in the day. Previously, people had just done single angle calculations, but they really moved this up to a supercomputing scale kind of problem. And I kind of want to walk you through how they did it. So really what you want to learn here today is, like I said, not every problem you're going to be handed in your life is going to be one you've solved already. In fact, what happens is that you tend to be working on something you like, and then someone points out there's some miserable problem that you need to solve before you get to do the physics that you want to do. And you have to actually just sit down and work out how you're going to solve that in order to finish your project. Or, as George was very fond of pointing out earlier, sometimes you work on a project because it's fun and nobody knows anything about it. And then the experimentalists catch up with you and actually ask you what the phenomenology is, and you have to come up with a concrete answer. So both of those things can actually add a lot of complication to your life. So what we're going to do is we're going to start with this very tough nonlinear neutrino flavor transformation problem and develop an approach for how to solve it. So just a little motivation about why we want to do this. Supernova are great engines for neutrinos. Their neutrino luminosities are 10 to the 53 ergs per second during some epochs. And the neutrino baryon processes are really the energy well that is driving this explosion. So Tony talked yesterday and the day before about how the vigorous convection that's going on in the supernova explosion is taking cold matter down close to the surface of that protoneutron star and then heating it up with this neutrino flux. And then those heated baryons are then convected back out to the shock front and deposit their energy. And kind of a fun order of magnitude estimation you can do is, how many neutrinos here does a baryon need to absorb in order to acquire enough energy that it can now be ejected from the supernova, or it can share this energy with other baryons it encounters and power the explosion? Well, a figure of merit is that the protoneutron star kind of metric deviation near its surface is roughly 10%. That means that any particle that gets down close to the surface of this protoneutron star needs to gain about 10% of its rest mass and energy in order to reach escape velocity. So 10% of a proton or neutron mass is about 100 MeV. And a typical neutrino energy that's being emitted from the core of this protoneutron star is about 10 MeV. So, figure of merit estimate, a proton or baryon needs to absorb about, proton or neutron, excuse me, needs to absorb about 10 neutrinos in order to be ejected. Now, you'd think that neutrinos don't see the matter, and to a large extent they don't, but there are so many neutrinos that a given baryon will see very many of them in its time spent down near the surface of the protoneutron star. But you can see that the main absorption channels here are flavor dependent, right? Neutrons like to absorb nu's, protons like to absorb nu bars. But if you do something strange to this flavor field, suddenly what you're doing, if you, say, take away all the nu e's and have only nu e bars emitted, you'll turn all the protons into neutrons, but then with no nu e's, there's no way to turn neutrons back into protons in the explosion time scale. So if you start playing with the relative fluxes between nu e's and nu e bars, it affects your heating efficiency immediately. Also, if you want to compute what your nucleosynthetic products here are, changing the neutron to proton ratio by 5–10% is the difference between having an R process and not having an R process in your neutrino-driven wind later. So it's very important to know what the flavor states of these neutrinos as they're emerging from the protoneutron star evolve into. So this is a slide that you've seen earlier, and this is a very nice, comfortable slide. So we have the basic schematic plane wave picture of how neutrino flavor evolution works. You have some wave function for your amplitudes to be in each of the neutrino flavor eigenstates. And then you have a very Schrodinger-like Hamiltonian equation. We like this equation. We've been solving it since we were undergrads. And so this is a very comfortable, calming, soothing thing to look at. You have a Hamiltonian that comes from the vacuum oscillation. You have a Hamiltonian that comes from forward scattering off of the background leptons. And you have a Hamiltonian piece that comes from the coherent forward scattering of neutrinos off of other neutrinos. But now what we're going to do that we didn't do earlier in the workshop is we're going to lift up the hood, and you're going to see all the ugly things and warts that you need to deal with when you're actually going about the solution of this problem. So we need to start with just the basics of neutrino mixing. Okay? We have neutrino mass eigenstates, which is how neutrinos propagate through vacuum. And because they're not coincident with the flavor interaction eigenstates, there just has to be some unitary mixing matrix that describes, conserving probability, how you map mass states 1, 2, and 3 into the weak interaction eigenstates, e, mu, and tau. And generally speaking, this has 4 free parameters. And you just write down a total mixing matrix that's just the product of the individual 2×2 mixing matrices that are unitary. And you wind up with this large block mess of sines and cosines. And so this used to be where all the fun was had. Not a lot of these mixing angles were measured, so you could go into regimes where it was actually easy to solve the mixing because there were symmetries that you could invoke here. But unfortunately, the experimentalists have caught up with this field, and so now we know what all of these mixing angles are. The CP violating phase delta is relatively unconstrained at the moment, but this particular set of mixing angles means there's no easy way to just ignore certain kinds of mixing. All of these mixing angles are relatively large. So we're going to have to keep this entire mixing matrix, and we can't split the problem into smaller chunks. And well, that mixing matrix isn't the only part of the story, because in order for neutrinos to mix as they propagate, they have to have mass. So we've measured the delta m squareds, the mass squared splittings. And to see why that drives neutrino flavor oscillation, you can just write down a simple plane wave solution for a propagating neutrino state. Right? We have our vacuum Hamiltonian here, and its eigenvalues are just the relativistic energy of the neutrino that's propagating. But neutrino masses are very small compared to their energies. So what we find is that in that limit, the eigenvalue for this Hamiltonian is more like p times m squared over 2 times the momentum. So we can write this down in a larger matrix format. And I've made an explicit split here, so you can see some of the phenomenology. So we have our neutrino mass eigenstate here, mass eigenstate ket, and there's a diagonal piece that's proportional to the identity matrix. And this piece is actually the completely uninteresting, boring piece of this Hamiltonian. All this is telling you is what the group velocity is of this propagating eigenket of the neutrino mass state. But what's interesting is that when you have mass differences between these individual mass states, this Hamiltonian has a piece that is traceless. There are different phase velocities between the different mass eigenstates of this propagating neutrino. So now you can see that if you have some mixed state here that isn't a single neutrino mass eigenstate, that it will pick up different contributions to its overall phase velocity as it propagates. And that will cause mixing. So neutrinos aren't actually born in mass eigenstates. They're created in flavor eigenstates of the weak interaction. So if you want to take this and then write down what it appears as in a flavor interaction eigenstate, like the interaction eigenstate you would be using in a supernova calculation. All you really need to do is just take this traceless piece of the Hamiltonian and then use your unitary mixing matrix to convert it. And so that's a miserable matrix that you don't ever want to look at, but thank goodness your computer can just do that for you. Now, the matter potential for neutrinos forward scattering off of electrons is even easier to deal with, because it's only the electron-lepton flavor neutrinos that can have a forward scattering with the background electrons that uses the W boson. So all the other neutrinos, they'll scatter off of leptons with the neutral current. They'll scatter off of baryons with the neutral current. But those are all diagonal elements in this forward scattering. And so remember, everything on the diagonal is just the group velocity, and we can throw that out. It doesn't contribute to mixing. So here we have our contribution. And again, we can take the traceless portion of this, and this becomes our forward scattering Hamiltonian for neutrinos propagating through a field of electrons. And you'll notice that this number density of electrons is now 3 coordinates in space. So this is, if we have some inhomogeneous distribution of electrons, this is going to be complicated to solve. And the story gets even more interesting. So in supernova, or the early universe, or the regions above accretion disks around black holes, there's a lot of neutrino emission. And when there's a large number density of neutrinos, what you can have is a neutrino propagating along can cross trajectories with another neutrino, and they will forward scatter off of each other. So because this forward scattering takes place through the neutral current and doesn't pull the weak interaction eigenstates of the neutrinos, you have no quantum mechanical handle on a measurement. It's a forward scattering event, so it doesn't change the trajectories or energies. So you have to keep track of the relative wave component phase information between the two neutrinos that have crossed paths. And the amplitude of this Hamiltonian contribution depends on the number densities of neutrinos that are on this trajectory and that trajectory. And you also have another piece here that's simply a geometric factor, what the intersection angle between these two trajectories are. And while it may seem mysterious, it's actually quite simple what's going on. If you have two relativistic particles and they're crossing paths, they're never going to see each other if they're moving collinearly, just because they're both moving at the speed of light in the same direction, so they have no cross-section to ever meet. So if you have an intersection angle where the cosine theta is equal to 1, there's no forward scattering Hamiltonian contribution. But if you crank that around and move head on, you now have twice the cross-section forward scatter. And if we only had 2 neutrinos, or 2 beams of neutrinos, this would be a tractable problem. But you have neutrino I comes out, crosses neutrino P's path. They forward scatter and change each other's flavor states. But things get more complicated when you add another neutrino to the mix. So now, OK, so I solved nu P and nu I, but now nu Q is coming along, and all right, it changed nu I here, but it changed nu P here. So I did this wrong because I forgot this neutrino. So now I have to go back and solve for this interaction, how that changed flavor states, propagate it to this one and that one. And there are 10 to the 47 some odd neutrinos being emitted from a supernova, and you don't want to try and backtrack 10 to the 47 times when you're solving these things. So you have to get a physical handle on a problem like this. And at the end of the day, I promise we'll get this down to only a few million to tens of million of nonlinearly coupled differential equations. But for the time being, let's take a look at how complicated this is just to start out. So we have our nice, fuzzy, warm Hamiltonian evolution equation. And our first variable we have to deal with is T, or R. It's the affine parameter along the neutrino's world line. So that's not going to be able to be gotten rid of, right? We're integrating along that. So we're always going to have some radial coordinate to deal with. Now we have the vacuum Hamiltonian. So it has energy, the neutrino mass state splittings, all the mixing angles in the CP violating phase. We have the electron scattering component. So that's a function of the electron density in the spatial coordinates where we're solving our problem. And then we have this piece, the neutrino-neutrino, component, which is a function of all three of the spatial coordinates where we're solving our problem, but it's also a function of the flavor states, the number densities, of a sum over all of the other neutrinos which have their own spatial coordinates and energies. So that's a mess. You know, nature only helps out a little bit. These things are the parameters that are set in the beginning of the problem. Everything else might need to be a variable. And if you count up, we have about 6 dimensions to deal with here. So we need to think physically about this problem. What are we going to do to simplify it to the point where we can, you know, not solve a 6-dimensional problem anymore, solve something a little bit more tractable? So point number 1, spherical symmetry is our friend, right? We're physicists. When we are confronted with something we don't like, we turn it into a sphere. And so we shall do the same thing here. And it's not such a bad approximation, truth be told. So the matter potential in spherical symmetry no longer depends on the azimuthal or polar coordinates, right? It's simply a radial function of the electron number density. And this is our protoneutron star sphere here. And so there's electrons out here. And that's helpful. And the reason we can get away with is if you think about the solid angle that, you know, all of the neutrino trajectories subtend tracing back to the surface of this protoneutron star, we're solving for what's going on a little teeny chunk of volume out here. And so this little teeny chunk of volume is actually going to be more or less homogeneous. Even though this whole supernova is a very non-homogeneous environment, the local environment where we're actually solving for what's going on with this tiny chunk of solid angle is relatively homogeneous. So we can reasonably close our eyes along a single line of sight and solve for what this Hamiltonian contribution is. So now, all right, we have to add in the neutrinos. And this is where everything gets complicated, obviously. We have neutrinos propagating along one direction in space, and then another neutrino propagating along a completely different direction, coming off of a completely different section of the protoneutron star. And it intersects at some point. And we need to, you know, work out what these Hamiltonian contributions are going to be. So just thinking geometrically, you know, we've taken the center of the system, it's spherically symmetric, but now we've moved off of a line of sight along an axis. So now it's not really spherically symmetric anymore, but it is axisymmetric. So you can think about, well, how am I going to get this intersection angle piece here? And so you write down the dot product of the two unit vectors that represent the trajectories. And you've got all the angles you need to keep track of. But you're axisymmetric. So pick an axis, and we'll see if we can integrate around it and achieve anything. And so we'll integrate around the azimuthal axis here. And it turns out that when you do that, integrate out one angle, that actually drops the dependency on all the azimuthal angles that you are considering. And so once you have invoked axisymmetry far away from the protoneutron star, suddenly now you're only down to 2 spatial coordinates that you have to worry about. The intersection angle of the 2 neutrinos with the z-axis as you're propagating outwards. Yes? Go ahead. Yeah. Yes. That is correct.
Right. So you're integrating out P.
Yes.
But of course, you're presuming something about the emission at the surface. So
that's right. No, so the emission at the surface is also axisymmetric.
Yeah.
Right.
And that's, of course, we know, it's problematic.
So I'm doing the 2006 version of this problem. So we only have 2.5 hours, Tony. I mean, no, I'm just teasing. It's OK. All right. So yeah, it is axisymmetric on the surface. So, well, but if you go to your 2-dimensional calculations and you go to the polar direction, then you're OK. Yes?
So, the neutrino which follows the straight line from the
It's following a geodesic. Yeah.
So, because there might be interactions, especially scattering.
Ah, well, yeah, so that's absolutely right. And so this is the 2006 version of this problem. So we're picking an epoch for this whole calculation that is the Kelvin-Helmholtz phase. There's not enough matter around to have a secondary scatter change trajectories later out. You have not a non-appreciable amount of return flux at this point. OK. So curved space is a very interesting question, and hasn't been tackled yet. Hasn't been tackled yet. It's going to be, yeah, it's good. 10%. Yeah, it will have more impact on the cross sections and the forward scattering potentials, I would think, than the actual trajectory bending. Yeah. 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 Yeah.
Not because if we start with the spherically symmetric initial state, trajectory bending will preserve that symmetry.
That's correct. OK. And so now that we've invoked axisymmetry, now we can actually start doing some basic trigonometry. Basic trigonometry will be our friend. So you can see for these two different neutrino lines that I've drawn here, the actual emission angle from the surface of this protoneutron star is identical for both of these two world lines. But this neutrino is intersecting our z-axis at a very different angle and radius than this second neutrino's spatial coordinate. But if you stare at this and draw triangles long enough, you'll discover a nice little relationship between the neutrinosphere radius and the emission angle and the radius at which a neutrino crosses our z-axis world line and the angle at which it crosses that line. So now what this allows us to do is we are taking our one of our spatial coordinates that we had to solve for, and we're turning it into a coordinate that's at the source. So now, rather than evolving two spatial coordinates simultaneously, we can evolve one spatial coordinate just by knowing about a bit of source geometry and keeping track of that coordinate, which isn't going to change as we evolve the problem.
So GR was basically just slightly modified this relation.
Correct.
But using the redshift.
Yes. So that helps us now with this piece here, this geometric piece. It's just an explicit function of one spatial coordinate and then two source coordinates that we need to keep track of. And basic trig is, again, going to be our friend. So we've got our Hamiltonian. We've worked out, we've simplified this piece as much as we can. And we need to understand now what our number densities are going to be, because we have our surface of the protoneutron star's neutrinosphere, and it's emitting neutrinos outward. But we need to quantify how many neutrinos are being emitted into what angle. So now we need to start thinking about binning this problem, right? We've got some emission bin, var theta I, but it has some width, all right? And that width is going to set the geometry of what the solid angle that the emitting surface is going to subtend and the path length from the source to our point where we're actually doing our calculation. And you need to know these two things in order to convert neutrino emission rate and luminosity at the surface of the protoneutron star into a number density, right? And you can see this is nice, right? This path length difference isn't actually very dependent on our emission coordinates once you're far from the surface of the protoneutron star, right? The path lengths for our neutrinos are going to be relatively similar so long as our radial coordinate is much, much larger than the radius of the protoneutron star itself. And I'm just going to kick one out to the audience now and see if anybody has an answer for this question. Looking at the equations that I've written down on the board now, what do you think a smart binning scheme for how we want to arrange our emission angle bins would be? What do you think is a good binning scheme? Here, I'll just take a poll. What's that? Constant d cosine theta. Nice guess. Not correct. All right. So this piece, the path length, is not actually giving us much information because it's relatively insensitive to our emission angle coordinates, right? R is going to be much, much larger than R nu. But this solid angle piece here is telling us something. So this denominator here, well, this is going to be a number that's close to 1, except right at the protoneutron star surface where it diverges, but we're not trying to solve the problem there. because, again, r is much, much larger than r nu. So this denominator is insensitive to our sources. But here we have emission angle coordinates. And so our differential piece of solid angle that we're emitting into is proportional to cosine theta d cosine theta. Well, what is cosine theta d cosine theta the derivative of? Cosine squared theta. That's right. So if we want each of our bins to make an equal contribution to the total number density that we're emitting from the surface of this protoneutron star, so that we're not wasting time making bins where there are not a significant number of neutrinos, what we can do now is just look at this and get a hint that if we bin evenly in cosine squared theta at the surface, then each of our bins that we create will contribute a roughly equal number of neutrinos to the evolution of this neutrino forward scattering Hamiltonian. All right, so now what we've done is, again, this number density now is an explicit function of one spatial coordinate and then two source coordinates, the emission angle and the neutrino energy that we're specifying for our emission spectrum. So let's go back, because we've made some progress. This is good. So here's our Hamiltonian equation. So we still have to have our affine parameter. There's no getting around that. And we have our vacuum Hamiltonian, which wasn't that bad to begin with, right? It's really only a function of energy. And we've convinced ourselves that the matter potential Hamiltonian, we can neglect two of the spatial coordinates and stick to r. And here with the neutrino forward scattering Hamiltonian, we can get rid of, with axis symmetry, one of these spatial coordinates and transform another set of these spatial coordinates into source coordinates. And that really helps now. So we've got two source coordinates that we need to keep track of, and then a spatial coordinate and flavor states. Really, that's going to give us the information that we need to solve this particular version of the problem. So this is getting manageable. So now that we're down to 3 dimensions, the affine parameter, the energies of the neutrinos, and their emission angles, now we can start thinking about how we're going to fit this problem on a supercomputer, because these are real machines. You only have so much memory to play with, and it matters that you don't explode their memory reserves. So if we write down what a individual neutrino energy and emission angle state is going to be, it's going to be 3 complex double floats for one neutrino flavor eigenstate, because you have the amplitude to be in the original flavor eigenstate, and then the coherence terms for transformation to the other flavor eigenstates. But then you have 3 different flavors of neutrino, and they each have their own amplitude to remain in their initial flavor state and then oscillate into other states. So that's a 3x3 matrix of double length floats that are complex. And if you actually compute how large that is on memory, it's about 288 bytes. And that's fine. That's nice and small. That's a reasonable amount of memory, even back in the olden days when dinosaurs roamed the Earth. But we now have to parameterize the remainder of the dimensions in our problem. So we're solving along the affine parameter, so that's kind of a scalable thing. But we're going to have to pick a number of cosine bins that we're emitting in, and a number of energy bins that we'll parameterize the fluxes with. Now, from previous work that was done with the single angle calculation, we know that there needs to be a few hundred energy bins parameterizing the emission angle, the emission spectra, in order to get numerically converged results. And I'll tell you right now that based on calculations we've done already, we'll need about 1,000 cosine angle bins in order to parameterize this. But what we can do is now parallelize along the emission angle dimension. So what we'll do is we'll spread our job out and only have one process, for instance, responsible for 1 or maybe 2 emission angle bins. And we'll have them talk to each other in order to solve the problem. And that makes the data load manageable, right? You really only have about 100 kilobytes per process just remembering what these flavor states are. And with modern memory, that's no problem. But the trouble that we get into is that neutrino self-coupling Hamiltonian, it needs each emission angle to speak to every other emission angle in the calculation. And that becomes a problem when you naively implement communications between your nodes, because you're not sending n cosine theta messages, you're sending n cosine theta squared messages. So now you're taking 100 kilobytes, sending it 1,000 squared times, and now you've blown up the amount of traffic on your network, on your supercomputer, that you need to execute in one step. This is bad news. You don't ever want to dump 100 gigabytes of data on a network in a single step. It will take, you can look at the specs on Gordon, and you will lament ever trying to do this kind of interconnect on that supercomputer. But we're going to be smart about this. So we can't just dump 100 gigabytes of data on the network at once. And Bronson actually gave a great quote, and I'm gonna keep this slide forever. Exploit data locality. This, yes. So now I'm gonna kick another question out to the audience. Here is our neutrino self-coupling Hamiltonian. What can we do with this Hamiltonian that will allow us to exploit the data that each process already has on it? Any guesses? So we're summing. So does that give you any hints? I'll reveal one hint. Right, this cosine theta ij, it's separable. Oh. Guessing? Come on, just shout it out. Oh, yes. We will, but without calling comms. Right, we're going to do this locally. We're trying to do this right now before we ever start talking to another node. How are we going to get our data traffic overhead down just on our single process? All right, here. There might be symmetry. There is. You know what it is? Multiplying by 1. I love multiplying by 1. I identify with it. All right. What we can do is actually perform part of this sum locally, just on a single node. Right, this piece 1, this doesn't care about any of this geometric gobbledygook. So whatever the neutrino flavor eigenstates and number densities that are already on our node, we can form one part of the sum here just at one shot. And then, because this part of the sum is separable, the node only needs to know what its own emission angle bin is. And the rest of this sum, we can just multiply this cosine theta times the other pieces of here, of this number density and flavor states, and create another sum. And together, these things are now down from 100 kilobytes to just 288 bytes we need to transmit. That's great. All right.
Because your Hamiltonian is a 4-vector and you have spherical symmetry, it only has 2 components. It has the radial direction and it has a timeline piece.
Absolutely right. That's why you can just sum on all of these things. So now we have only 288 bytes we need to transmit. And now you are right, sir. We will perform an all reduce. So this is great. So we have n cores, about 1,000 of them, and 288 bytes to transmit per core. Order 100 kilobytes of total data. And all reduce is smarter than us ordinary humans. And so it won't try to do what I was originally promoting and send every single piece to every single process. It'll pick a process, gather the data, and then rebroadcast it. So now what happens, you call all reduce. And the sums from each of the individual processes are now combined into a single sum that's given to every process. And so now you have 2 pieces. And if you want to know the Hamiltonian contribution from neutrino forward scattering on your own process, well, you just need the sum from this guy. And then you need to know what emission angles you are in charge of. And then the sum from the master process, the second piece of that sum. And Peter Sellers really likes this. All right. So now we have this down to a single process size problem, right? We've collected all of the neutrino wave function information that we need to take the set of wave functions that's resident on a local process, right? 3 by 3, and then times 2 because you have particles and antiparticles. And then you have however many energy bins, a few hundred, different sets of these equations that you have to solve now. So that's a few thousand, coupled ODEs per core. That's you could run that on your laptop. Mathematica wouldn't balk at that. And well, this is tempting. because we see this and we're comfortable with this and we're lazy, and so we crack open numerical recipes. And the form of this, it's some nonlinear equation, so you probably want an implicit solution scheme. And numerical recipe says, oh, well, first order implicit solution methods are guaranteed to converge, right? So let's just write down our first order implicit solution method for our Hamiltonian. This is wrong, wrong, very, very bad, 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 and we're not going to do it. And let me explain to you why. So why does the obvious thing to do fail? So we wanted to use numerical recipes, right? So we'll write down our first order implicit solution method, and you have to have some form of leapfrog algorithm because it's a nonlinear equation. You can't really check the answer against some analytic method for solving it. So you have one step where you take the initial wave function, you compute your Hamiltonian contributions, and you evolve to a final state. And then this particular leapfrog I've diagrammed here is called the Hoynes method. You start again, use half a affine parameter step, and then you make a new Hamiltonian that averages together the initial state and then the first state that you solved the first time to get a second state. And this state's in the midpoint. And then you take this wave function and the original wave function, and then you do another half step to get to a new final state. And the average of those two is used. And so at any one point, you really need to keep 3 of these in memory. But again, you have 100 kilobytes of worth of data for a single emission angle bin. You need 3 copies of different steps of this integration. 300 kilobytes isn't going to kill you as long as you're keeping it on a single process. So this is all right, it seems. But if you try to use an implicit, just an ordinary first order implicit method, you'll find that the local solutions kind of look like this. The complex phases of these wave functions are oscillating like the diagonal elements of this Hamiltonian. And near the surface of a protoneutron star, neutrino fluxes are large, electron number densities are very large, and those oscillation lengths are very, very short, 10 centimeters, which is very bad news if you want to solve for the region of neutrino flavor transformation. And you can infer that just from the ranges where these forward scattering potentials are the right order of magnitude to give some kind of flavor transformation phenomena. And you need to cover a distance of 1,000 kilometers or so or more. And when you look at what the error is from a simple integration method like this, you find that the error on a single wave function kind of goes like the integration step size over this oscillation length. Well, you want a nice tight error tolerance. You want 10 to the minus 6 because you have wave functions here. And it's bad mojo if your wave functions no longer have a norm of 1 because you were sloppy with your error tolerance. So you want tight error tolerance, but then suddenly your delta R step is now 1/1,000,000th of this oscillation length, which was already 5 orders of magnitude smaller than you needed for your integration. So now you have 10 to the 13 steps you need to do. And you don't have enough computer time ever. There simply isn't enough. So we need to think physically about what we're going to do with this equation because it's a Hamiltonian equation. And well, when was the last time you computed an eigenvalue? Well, the last time you probably found a Hamiltonian equation you had to solve. And so maybe the solution method here would work best if we actually went and computed the eigenvalues and eigenvectors of this Hamiltonian. So that's actually a well-known method for solving implicit ODEs called the Magnus Method. And so here we have just a description of it. We have the wave function at r plus delta r is now the exponentiated Hamiltonian matrix times our distance step that we're making, and then that quantity times our initial wave function. So in order to exponentiate this matrix, we need to solve the eigenvalue equations for our single Hamiltonian, right? For our one energy angle bin on our main process. And then once we have that, it's very straightforward to show that the exponentiation of this matrix gives you a matrix form of the eigenvalues and eigenvectors that we can then multiply through. And this is computationally expensive. But the potential here is that because we're being smart and looking at the symmetries that are intrinsic in our Hamiltonian, that we might be able to get away with taking a much larger step size. And kind of a nice point is that back in 2006, when the UCSD cycling team actually had to power a dynamo to run the supercomputers around here, and GPUs weren't particularly common, the codes that were written back then actually just sent this problem a few hundred times to the main core. But now that you have GPUs available on most supercomputers, this is actually a poster child for a problem that is very easy to implement on a GPU. You have a few hundred of these Hamiltonians, but they're each only about 288 bytes. A GPU core can remember 288 bytes and then follow a script that takes it through all of the individual steps, and there are many of them that you need to diagonalize a Hamiltonian matrix and compute what its eigenvalues and eigenvectors are. But because you can send this to a GPU, and they have lots of individual cores, lots of threads, this actually is a very easy portion of this problem to compute locally with a GPU. And so Bronson, again, mentioned Magma. Yeah, look it up. It's good stuff. So why does this work so well? Well, to visualize the Magnus method, I'm going to take a quick break, aside really, and say there's a very old trick for dealing with wave functions. You can turn a complex valued wave function into a orthogonally geometric object. So you take an SU2 object and turn it into SO3 object, which is unit norm three-dimensional space, just by taking an inner product with the Pauli matrices. And that gives you a nice way to visually represent the Hamiltonian that we've been trying to solve. But what we're really solving with the Magnus method is not this Hamiltonian anymore. What we've done is we've gotten rid of the Hamiltonian, and we've replaced it with the eigenvectors of the Hamiltonian, which we can also form just to get a visual representation from taking this inner product. And we've gotten rid of our wave functions, and now we have a isospin vector for our wave function that is oscillating around this eigenvector with not the oscillation frequency that comes from the Hamiltonian matrix, but from the eigenvalue that is associated with that eigenvector. And if we are in a regime where these eigenvectors and eigenvalues are constant, that being there's nothing dynamically interesting going on with this wildly large system of coupled ODEs, they're just kind of sitting there spinning around, we can get away with taking large steps, because if V remains constant in its direction and magnitude, and the eigenvalues that associate it back to the Hamiltonian matrix are relatively constant, these things will just, every time you take delta R and delta R over 2 twice, you'll always wind up back in the same position. And that's why we can get away with taking much larger step sizes. We still have our basic integration algorithm, where we're taking our leapfrog steps and averaging together our wave functions at different stages during the evolution. But now, instead of trying to beat the system into submission by solving the Hamiltonian directly, we're being smart about this and looking at the eigenvectors and eigenvalues, and we're rotating our states around them. And that allows us to get away with having an error that's still tight, right? You still want a tight error, but these eigenvalues can have much, much lower amplitude than the diagonal elements of the original Hamiltonian. So this can be a much larger number, and the eigenvectors may not be changing very rapidly with radius. So what you find is that typically you can get away with radial steps that are actually longer than the oscillation length of the individual neutrinos in the problem. And typically, you can get away with about 1 million steps. And so now this is doable in a machine reasonable amount of time. 100 milliseconds to do a leapfrog algorithm and do all of the communications that you need, times 1 million steps is order 10 hours. So that is what you need in order to actually start building a code that can solve this problem. Typically 1,000. Yeah.
So I understand what you're doing from a spatial standpoint. So we've assumed some symmetry, and that's cool.
Yes.
And there's, of course, a perfect match if we have imposed that T-symmetry, regardless of what's happening spatially.
Yes.
What about time dependence? What about rapid time dependence?
So as long as you don't have the return scattering like you do in the halo scenario, what's going on an individual neutrino's world line is that it's an ultra-relativistic neutrino, so the lapse of proper interval is 0. So from its perspective, the envelope is standing still. So you may need to write down, for instance, if you have a rapidly evolving matter field, you could write down a retarded matter potential that actually tracks the motion of the field as that neutrino is propagating outward. But from the neutrino's perspective, the matter isn't moving at all, right? There's a static field that it's propagating through because it's moving on a light-like trajectory.
Tony, very briefly, this is more like a steady state problem.
It is a steady state problem.
You try to
Yeah.
think about it is that this thing goes on forever. Neutrino velocity doesn't change at all. And so each individual neutrino is stepping through this spatial thing, but it's also connected with the partial t with its own velocity.
Yeah.
It's a steady state.
Yeah. But this is actually, now we have a plan. So now we've walked through this miserable problem, but we've gotten it down to a very manageable size. So just remember, yes.
To some extent, we are a little bit worried about, we should be physically worried about one thing, which is we are kind of building in a time-independent state.
Very true. Very true. Yes.
Now, we don't really know. We could find the solutions, JJ will show you.
Yeah.
Right? But
I would,
actually, find solutions.
as Alex and Huayu have showed already, this is the last slide of my talk. So we've come to the end.
You've already seen the problem.
Yes.
There are solutions. But you have to wonder if there are other kinds of solutions. Which
That's
are
right.
not steady state.
And that's exactly what we worry about with the halo, Tony. The possibility that you have, the return flux now gives you more information about what was happening out in the envelope. It comes back, and now the standing wave solution isn't stable anymore. The returning flux remembers what the standing wave solution was coming out, but it might change the standing wave solution when it comes back. So that's a much more complicated problem. You can't do a lot of the tricks that were done just now on the board here. You can't throw out anywhere near as many spatial coordinates. But yeah, so just remember, look for symmetries, because symmetries help, especially when you're solving multidimensional problems. And be efficient with your memory, with your message passing. Do as much calculation on a single process as you can, and exploit your GPUs, because they're handy. And lastly, don't forget to think physically, because we're physicists. So if you see a problem that looks like something you've solved before, you should probably investigate why it was that the particular symmetries of that problem are showing up again. And so we had a Hamiltonian-like matrix, and the solutions, it turns out, follow local eigenstates of that Hamiltonian. Even though it's a nonlinearly coupled Hamiltonian, there are still local solutions that make the integration of the equations of motion much quicker.
That seems interesting, actually. So, so basically what you do is you use the neutrino state at a certain radius to calculate the Hamiltonian, and you diagonalize this Hamiltonian.
Yes.
And you take this giant step forward in which those neutrinos might oscillate a few times, right?
Yes.
And so, of course, even the Hamiltonian, since it's nonlinear, will be oscillating together with the neutrinos.
That's correct.
Well, that's the case, and step still works.
So the individual phases don't affect the eigenvectors and eigenvalues of the Hamiltonians so much, and that's what saves you. So if the nonlinear equations, if the evolution is picking up on those phases and causing those vectors and eigenvalues to change and rotate, you no longer have this wonderful regime where your step sizes can be very, very long compared to the oscillation length. Then you do have to slow down. But you're not wasting time in a regime where nothing is going on, just watching phases oscillate. Yeah. All right. Yes? Yeah. Yes. So that is, well, actually, it's Huayu can actually talk a little bit more about his experience using GPUs. So the older ones, yeah, not so great. I know, and the history behind that is actually kind of cute. The older cards were actually created to do fast Fourier transforms for video games. And actually, the interesting thing about doing fast Fourier transforms for video games is you want to generate the output video signal. And if you drop a bit in an FFT, it actually has very little entropy. And so that when you take the FFT and then convert it back into an RGB value on a screen, you've only changed the color of a pixel by a little tiny bit. So the old video cards, they didn't really care whether or not they had a crummy bit flip rate or bad leakage currents, because those FFTs were very resistant to gaining entropy from bit flips. Stupid video games.
You know, I'm still trying to wrap my head around the whole stationary state thing. I mean,
Yeah.
stationary state, generally speaking, only works when, you know, you have discrete time scales, right? Where you
Mm-hmm.
have, you know, the time scale for, say, the mediums is long, the change in medium is long. And you
Yes.
have the time scale for the radiation field,
Which is why we thought this was a reasonable approach.
yeah.
Yeah.
But, I mean, bottom line is, you're looking at this environment, right,
Mhm.
around your current, so in a supernova,
Yeah.
like if I'm really thinking about doing this in situ in a supernova, you know, my neutrino source
Mhm.
is very time dependent. It's time dependent, but, you know, pick an angle, it's angularly dependent,
Yep.
and, you know, it's time dependent, both. So at a given angle, it depends on time. If you go across angles, it depends on angles, and that depends, changes in time. So
It's very much alive, yes.
okay? So, you know, I'm trying to understand how you can assume that, you know, you can use the stationary as if you're dealing with a true stationary state.
So,
Not to mention that, strictly speaking, if we're dealing with neutrino mass, ones are massive neutrinos,
mhm.
we don't have to talk about affine parameters, right? I mean, these are, ES is not zero for these particles.
Yeah, we just want a
We just want
consistent
yeah.
parameter along each
world line. That's right.
Yeah, so we can compare those world lines in a way that we can, you know, get accurate phase, lapses of phase along each world line.
Yeah.
Because we need to look at interference.
That's right. I mean, that is what we're tracking. And so, so Tony, I think that in terms of the timing, what the relevant time scale is actually the difference in propagation time along a pencil of directions. So the neutrinos that are emerging from the surface of the protoneutron star, you're right, the conditions at that surface are changing rapidly, but most of the flux is outwardly directed. So what you're really comparing are the time of flights for a neutrino that's emitted radially and a neutrino that's emitted tangentially from the surface of the protoneutron star. So as long as those time of flight differences are small compared to the dynamical time scale, then the stationary solution is at least valid for problems where you're solving the outward radially directed coordinate, right? So if you have one neutrino, here, let me go back. We'll use this slide. Okay. So you have a neutrino here that's emitted more or less tangentially, right? And a neutrino that's emitted more or less radially right here. And so the only thing that we need to worry about in terms of whether or not we had the right emission physics at the time those two neutrinos left the surface of the protoneutron star is kind of the difference in the time of flight along that line versus that line. And so So the path length difference between the different emission trajectories, here it is, right, is right here. So the further away you get from the surface of the protoneutron star, the better the approximation becomes. But you're absolutely right. When you're close, yeah. Yes. That's right. Yeah. So, you know, what's the... So, Alex and YU, do you guys want to come up? Because this is kind of the informal question-answer session anyway, so...
Well, Alex just said that you're also neglecting
That is true. Yeah. Yeah. Now, axisymmetry. Now we can. One of the things we've done. You still you can still keep axisymmetry, but not all of this. Not all of the simplifications are necessary. You can parameterize the emission differently based on the different emission locations. So the different emission angles can have different spectra for relatively little memory overhead and no increase in the amount of flops that you need to perform.
But if you had, you could still use the stationary state treatment, just that you have more spatial dimensions to worry about.
That's right.
You can break the symmetry and still assume the stationary state is the way you solve it.
Yeah.
Of course, again, let me just say that we are, building in these.
Yeah, we are building in these symmetries. Right.
And there's interest in whether those symmetries can be effectively spontaneously broken by the neutrino-neutrino interaction itself.
Yeah.
There are several papers on this by Magnus et al. And by Ravel
Mm-hmm.
and these are not numerical computational studies that capture all of the nonlinearity. They're essentially, stability analyses that are fairly abstract.
Yeah.
But they suggest that you might actually even break the spherical symmetry, for example, just spontaneously because of the neutrino-neutrino interaction.
Yes.
Then the halo neutrinos, the differences in flight time can be in the order of milliseconds.
And that is absolutely a macroscopic time scale. Yeah. And so the steady state approximation just doesn't apply there. That's right. All right. Well, thank you guys very much.